In today's talk, we will give some technical lemmas for our computations. First, let's look at some motivations. So this is a picture of the end of E2 term around the 30 steps. Using secondary operations, it's not hard to establish these blue D2 differentials. Now, we want to ask a particular question. So how can we prove this particular red D3 differential? So here's one way we want to make the argument. First, we have this D2 differential from H5 to H0, H4 squared. This is a half invariant 1 D2 differential. And now we have a new extension from this blue point to this black point. That's a H2 extension on the E2 page. And then moreover, we look at the random spiral sequence for co-fiber of nu. Here we have a D2 differential from that particular black point to this red point. The red point we can read off from the data, then take the H0P from the bottom cell. And we can also find that the black dot comes from the top cell, which corresponds to this black point, which is H0, H4 squared. Now, from this differential in co-fiber nu, we can argue that they actually hidden nu extension from this black dot to this red dot, because this red dot corresponds to this red dot in the bottom cell, and that black dot corresponds to this black dot on the top cell. So we have a hidden nu extension from this black dot to this red dot. Then we can apply Leibniz rule, because we have a D2 differential here, and we have a nu extension from this dot to this dot, and another hidden nu extension from this dot to this dot. And using the Leibniz rule, we will argue that we have a D3 differential. This is some kind of naive arguments using hidden nu extensions. But the naive argument does not always work. This is a familiar part around the 14th step, where the first end of differentials shows up. We have this D2 differential from H4 to H0, H3 squared. Now we can argue like this. This black dot, which is H0, H4 squared, does not have any non-trivial 2 extensions, because all the candidates are already 2 multiples by something in higher filtration. So by the definition of 2 extensions, this black dot does not have any 2 extensions. So can we argue that because we have this D2 differential and this black dot has a non-trivial 2 extension to this dot, and this black dot has a trivial 2 extension, so can we conclude that that dot, which is H0, H4, supports a trivial D3 and D4 differential? That is not the case. So our naive argument fails in that particular case. So we want to ask, under what conditions can we make these naive arguments? When they work, and if that works, what is the indeterminacy of the results of these arguments? We need to be very precise with these problems, because we want to apply these arguments using a computer program. Any tiny mistake of this problem will be amplified by the computer program. So we want to be very precise on precisely what condition we need and precisely what result we obtain. First, let's introduce our basic notation for the non-trivial extensions. We use the language of extension spectral sequence. Suppose we have a map between spectra f, x, and y. Then we have a complex of homotopy groups from 0 to pi star x to pi star y to 0. And then we filter pi star x and pi star y with the Adams filtration. Then there's the induced spectral sequence. We call this induced spectral sequence the F extension spectral sequence. That has E2 page, that has E0 page, the E infinity page of x and the Adams E infinity page of y, which converges to the kernel of pi star of f and the co-kernel of pi star of f. We can see that the D0 of this spiral sequence is induced by f on the E infinity page of the Adams spectral sequence. Differentials in the Adams spectral sequence has a form which goes from dnf goes from ENST to ENS plus N T plus N. That En refers to the En page of the F extension spiral sequence, which are subquotients of the E infinity term of the Adams spectral sequence. Then we say that there is an F extension from x in the E infinity page of x to y lying in the E infinity page of y if there is a F in the F extension spiral sequence, there is a differential from x to y. We say that F extension is essential if y is non-trivial is in the En page of the F extension spiral sequence, which means essentially that y is not hit by any extensions of higher filtration. Otherwise, we refer to it as inessential. Now we need to introduce the notion of crossing differentials. Suppose x lies in the Adams E infinity page, E infinity st of x. We say that F extension dnf of x equal y has a crossing that hits Adams filtration p for some p less or equal than s plus n if there exists an element x prime lying in the Adams E infinity page E infinity s plus a t plus a of x with a greater than 0 and a f extension from x prime to y prime for some non-trivial y prime lying in the E infinity page E infinity s plus a plus m t plus a plus m of y such that the annual filtration of y prime equals p, which lies lower or equal to the annual filtration of y. So that's a notion of a crossing differential. We say that a f extension from x to y has no crossing that hits a range annual filtration greater or equal than p if there does not exist element x prime lying in the E infinity page E infinity s plus a t plus a with a greater than 0 and a f extension from x prime to y prime for some y prime lying in the E infinity page E infinity s plus a plus m t plus a plus m of y such that p is less or equal than the annual filtration of y prime, and also the annual filtration of y prime is less or equal to the annual filtration of y. We say that a f extension from X, Y has no crossing. If it has no crossing, then its range annual filtration greater or equal than the annual filtration of X plus Y. So here's the illustration of a crossing differential. Suppose we have a f extension from X to Y. That is a long arrow, which goes from E infinity of X to E infinity of Y. Then, if some shorter f extension differential from X prime to Y prime hits crosses this long differential, then we say here's a crossing differential. And when the target of this crossing differential lies in annual filtration P, then we say that's a crossing in annual filtration P. And from this definition, we say that no crossing differential that hits a range annual filtration greater or equal than P means that this crossing differential does not hit this gray range. So why is the notion of crossing condition very important? That lies in the fact that with the no crossing condition, we can say that anything represented by X has the expected extensions. So more precisely, suppose a f extension from X to Y has no crossing in the range of annual filtration greater or equal to P, if and only if for all X represented by X, such that the image of X under the map F has annual filtration at least P, then we conclude that the image of X under F is detected by Y. In particular, we have that f extension from X to Y has no crossing if and only if for any representative of X, we have fx is detected by Y. And f extension from X to 0 has no crossing if and only if for all representative of X, the annual filtration of fx lies in annual filtration greater than annual filtration of X plus n. And moreover, we conclude that if the annual filtration of f equals n, then all the dn f differentials have no crossings in the f extension spectral sequence. And using the non-crossing condition, we have a commutativity of extension spectral sequences. So we consider a homotopy commutative diagram of spectra like this. Now suppose we have elements x, y, z, w in the E infinity terms of x, y, z, and w. Now we suppose there is a f extension from x to y, and also a p extension from x to z. So f extension from here to here, and a p extension from here to here. And moreover, we suppose that the differential in 1 or the differential in 2 has no crossings. And then we also suppose there is a dlj extension from z to w, which has no crossing that hits a range of anomalous filtration greater or equal than s plus n plus k. So there is a j extension from here to here. And moreover, we suppose dk minus 1 of q y equals 0, and that has no crossing. So that means the target of y on the q has a annual filtration at least k higher. Then we conclude that there is a q extension from y to w. Here is the illustration. Suppose we have a f extension from x to y and another p extension from x to z. And these two extensions, at least one of them has no crossing. And also we suppose there is a G extension from Z to W. And then we suppose that this extension has no crossings in this gray range. And moreover, we suppose that any candidate, any representative of Y has Q extensions always lie in this gray range. Then we can conclude that there is a Q extension from Y to W. And you can see that in order for this theorem to be true, we need some crossing conditions. So the essential part is this. This non-trivial extension from X to Z means that there is some choice of X whose image on the P is detected by Z. And also, this extension from X to Y means there is some representative X whose F image is detected by Y. Then we use the non-crossing condition to make sure that there is a common choice of representative of X, which has P image detected by Z and its F image detected by Y. And also, we need the non-crossing condition for this extension from Z to W to conclude that with our choice of X and its image on the P gives a particular choice of Z, we want that particular choice of Z has J image detected by W. So that's how we use the non-crossing conditions here. Next, let's review the theory of synthetic spectra. The stable symmetric monoidal infinity category of HF2 synthetic spectra is constructed by Pstrogowski along with a functor nu from the classical spectra to HF2 synthetic spectra. That functor is length symmetric monoidal and preserves filtered colimits. However, nu does not preserve co-fiber sequences in general. We can define the bar-graded synthetic spheres as with superscript SW, which is defined to be the S minus W suspension of nu SW. There is a natural comparative map from S0 minus 1, which is a suspension of nu S minus 1, which goes to nu of suspension S minus 1, which is S0, 0. Then lies in the category of HF2 synthetic spectra, and we denote this map by lambda, which is the pi 0 minus 1 stem of the synthetic sphere. We denote by S00 modulo lambda the co-fiber of lambda. And for every n greater or equal than 1, S00 modulo lambda to the nth power, that is the co-fiber of lambda to the nth power. Then we can prove that it's an E-infinity object in synthetic spectra. Now, suppose we have a distinguished triangle of spectra from X to Y to Z to the suspension of X. In general, if we apply the function nu, we do not get a distinguished triangle of synthetic spectra because nu in general does not preserve co-fiber sequences. But suppose we have the random filtration of H is greater than 0, and consequently we have a short exact sequence of HF2 homology. Then we can construct a distinguished triangle of synthetic spectra from nu X to nu Y to nu of Z, and then to suspension 1, 0 of nu of X. So the point is this: because the annual filtration of H is positive, then nu H is divisible by lambda, and we let H hat to be the nu H divided by lambda, and we can prove that using H hat instead of H, there is a synthetic distinguished triangle. And using the language of synthetic spectra, we can interpret classical Adams differentials as a lambda box type. We consider the map delta from cofiber lambda to the n to the cofiber of lambda to the m minus n, which is essentially the boundary map in the lambda box type spectral sequence. Suppose we have a dr differential from x to y in the classical Adams spectral sequence. Then, if r is greater or equal than n plus 1, then we have a delta extension from x to the lambda to the r minus n minus 1 multiple of y. And if r is less than n plus 1, then we have a delta extension from lambda to the n plus 1 minus x power times x to y. So that means essentially a non-trivial Adams differential corresponds to a non-trivial lambda box type differential with corresponding length. Now we can give a notion of crossing differentials. Suppose that r is greater or equal than n plus 1, and we have a dr differential from x to y, with x lying in the E2 page of E2 as t of x, the y lying in E2 as plus r t plus r minus 1 of x. Then a crossing of this dr differential on the En plus 1 page refers to an essential Adams differential dr minus a minus b from x prime to y prime, where x lies in E2 of s plus a t plus a, and y prime lies in E2 s plus r minus b t plus r minus b minus 1, such that a lies between 0 and n minus 1, and b lies between 0 and r minus n minus 1. And we said the Adams differential drx equal to y has a crossing on the En plus 1 page if and only if the corresponding delta n extension from x to lambda r minus n minus 1 of y for this boundary map delta n has a crossing. So we define the crossings of Adams differential in terms of the crossings in the delta n extension spectral sequence. So here's the illustration of crossings. Suppose we have this long differential from x to y. Then we say it has a crossing on the En plus 1 page if there is some x prime supporting a differential to y prime, such that the shorter differential crosses this long differential, and moreover, that x prime lies in this gray box, and the y prime lies in this gray box. So this is the definition of crossing differential translated from a crossing in the delta n extension spectral sequence. Next, we look at the notion of extension in the ER page. Suppose we have a map between classical spectra from x to y, and then we can consider the associated synthetic map f hat from nu x to nu y. So if the annual filtration of f equals 0, then we let f hat to be nu of f. And when the annual filtration of f is positive, then we take f hat to be nu over f divided by lambda. Now, for any r lying between 2 and infinity, we denote the following mod lambda to r minus 1's reduction maps by f hat r minus 1, which goes from the nu x suspended with weight e over f modulo lambda to r minus 1 power, which maps to nu y modulo lambda to the r minus 1 power. So essentially, f hat r minus 1 is a mod r minus 1 reduction of f hat. Suppose x is a r minus 1 cycle of x, and y is a r minus 1 minus n plus ef cycle of y for some ef less or equal than n less than equal than r minus 2 plus e of f. So n lies between this range. We say that there is a FER extension from x to y denoted by dn FERx equals y if there is this synthetic f hat r minus 1 extension from x to lambda to the n minus ef power times y. So essentially, FER extension means a synthetic extension from x to certain lambda power of y, which exactly what power depends on the weights of x and y. So we say that this FER extension is essential if the corresponding synthetic f hat r minus 1 extension is an essential differential in the f hat r minus 1 extension spectral sequence. So here is the illustration of a DNFER differential from x to y. So the condition is this. So in the random spectral sequence, we require that x survives to the ER page. So any differential supported by x has length greater or equal than r. And also we suppose y survives to the r minus n plus ef page. And then on the E infinity page of nu x modulo lambda r minus 1, this x survives, and this lambda to the n minus ef's power times y also survives. And then we say an extension on the ER page from x to y means the extension of this mod r minus 1 reduction of the synthetic map has a f hat extension from x to y. So that extends the classical notion of f extension because in the synthetic setting, on the ER we can talk about extension on the ER page because the ER page makes sense as something in the E infinity page in the synthetic setting. And then we have a notion of a crossing extension. The crossing of the FER extension from x to y is defined as the essential FE r minus a extension with some a lying between 0 and r minus 2. And also for some b lying from 0 to n minus a minus e over f, from some x prime to some y prime. And also we require that extension is essential in the sense that y prime should survive to a classical randoms E r minus n plus b plus ef page, and it should not be hit by random differential of length at most 1 plus n minus b minus ef. So that's an illustration of a crossing of a FER extension. So suppose we have we have a f extension on the ER page from x to y. That crossing means the essential extension from x prime to y prime. And moreover, we require that x prime survive to the E-A page and y prime survive to the E-N plus B plus EF page. And moreover, we require that y prime is not hit by differential starting from essentially from the filtration of x or one lower, depending on EF being 0 or 1. So that's a crossing extension. And that complicated notion of crossing for the FER extension is exactly the same as crossing in the synthetic setting. So a FER extension from x to y has a crossing if and only if the synthetic f hat r-1 extension from x to lambda to the n minus EF's power times y has a crossing. So that is the same as a crossing of the synthetic extension spectral sequence. Now we can state our generalized Leibniz rule. Let F be a map between two classical spectra. Suppose the following conditions hold. First, we require that there is a dr differential from x to some x infinity, and we suppose there is a FEN extension from x to y, and we also suppose there is a FE infinity extension from x infinity to y infinity. Moreover, we suppose that either 1 or 2 has no crossings, and moreover, we suppose that the extension in 3 has no crossing. Then we conclude that there is an Adams differential from y to y infinity. So here the illustration of the generalized Leibniz rule. So suppose we know all these blue D2 differentials. We want to show that they are non-trivial D3 differential like this. So what do we want to show? First, we have this D2 differential. Okay, that D2 differential can be shown, for example, using secondary operations. And then we have this non-trivial new extension from that blue dot to that black dot that happens on the E2 page. And we will show shortly that there is a hidden new extension on the E infinity page from that black dot to this red dot. So in order for this non-trivial extension to make sense, we need to use the synthetic setting, because on the E infinity page of the classical sphere, that point and that point dies, so the extension means 0 equals 0, which gives no information. But in the synthetic setting, this D2 differential in the classical Adams spectral sequence really means that in the synthetic sphere, there is a lambda torsion left on the target of this classical Adams differential. So on this black dot, there is a lambda torsion. On this red dot, there is also a lambda torsion. And we can show that on the E infinity page, there is a non-trivial new extension between these lambda torsion points. And then we will apply our generalized Leibniz rule. Let's check the non-crossing condition. First, we want that the original D2 differential has no crossing. That corresponds to that D2 differential. And we know D2 differentials in the Adams spectral sequence can't be crossed, because by our convention, crossing means shorter differential cross the longer differential. So the D2 differential is already the shortest differential that can't be crossed by shorter ones. And next, we want to show that the extension from X to Y is not crossed. And also, that means extension from that blue dot to that black dot. Because the map F, which is multiplication by new map, that lies in the annual filtration Y. So we have shown that if a map has annual filtration Y, then any extension which raises the annual filtration by Y can't be crossed because we have no shorter crossing possible. Because no shorter extensions can exist because it's already the shortest. Okay, so the second extension has no crossing, and the third one, which means D2 differ, which means hidden extension from that black dot to that red dot. This is really what could have. So we can't exclude the possibility of crossing by formal reasons. We need to check precisely what happens. So from the diagram, the only possibility of crossing of this hidden new extension is by a new extension from this black dot to this red dot. So if there is a new extension from this dot to that dot, that is a crossing. But this new extension can be checked on the E2 term, and we can see directly from this picture that there is no such new extensions. So that means the new extension from that dot to that dot is not crossed. So all the non-crossing conditions are checked, and we can use the generalized Leibniz rule to conclude that because we have this D2 differential, we have this hidden new extension, we have this new extension, so that we can conclude there is a non-trivial D3 differential. And on the other hand, we have the following counterexample. If we start with this D2 differential, and we know that the two extension on that point is trivial, and the two extension on that point is this point. So why there is the existence of a non-trivial D3 differential does not contradict our Leibniz rule? That is because we have a non-trivial crossings of this extension. So there is a trivial 2 extension on that point, but we also have a non-trivial 2 extension from that blue point to this black point. And by definition, this short 2 extension crosses this long trivial extension. So that trivial extension is crossed by this non-trivial extension. That means precisely that for some choice of this blank dot, there could be a non-trivial extension from this dot to this dot. Because if some choice of this dot goes to 0, then the sum of these two dots go to this point. And that's precisely what happened, which gives us a non-trivial D3 differential possible. In order to apply the generalized Leibniz rule, we need an effective way to compute F extensions. We can do this using the generalized Markov trick, which gives a correspondence between a non-trivial extension and the Adams differentials in the cofiber. Suppose we have the following setting. We consider a distinguished triangle of spectra from X to Y to Z to the suspension of X. Suppose that EF plus EJ plus EH equals 1. That means that exactly one of F, J, and H has annual filtration greater or equal than 1. And the other two has annual filtration 0. Now suppose R equals N plus M plus L, n1 equals n minus e of f, which is greater or equal than 1. m1 equals m minus e of j, which is greater or equal to 0. And L1 equals L minus e of h, which is supposed to be non-negative. And we suppose x lies in the annual sequence, which is a n1 cycle, which lies in Zn1 s plus L t plus L minus 1 of x. Y lies in Zm plus 1 s plus n plus L t plus n plus L minus 1 of y. So y is a m plus 1 cycle. And x bar lies in Z r minus 1 st of z. So x bar is a r minus 1 cycle in Z. And y bar lies in Z infinity s plus r t plus r minus 1 of z. So y bar is a permanent cycle in Z. Suppose that there is a DL of h er prime x bar equals x. So this is the h extension on the er prime page from x bar to x, where r prime equals r minus m1, which also equal to m1 plus l1 plus 1. And also, we suppose there is a dr differential from x bar to y bar. Recall that x bar and y bar are classes on the random spiral sequence of Z. So we suppose that in Z there is a dr differential of the random spiral sequence of Z. And also we suppose there is a GEM1 plus 2 extension from Y to Y bar. And we suppose that the HER prime extension in 1 has no crossing, or the Adams differential 2 has no crossing on the ER prime page. Then we can conclude that X is a n plus m plus e of h cycle in X. And also we have a non-trivial f extension from xy modulo certain boundaries. So modulo br prime s plus n plus l t plus n plus l minus 1 of y. So modulo the targets of differentials shorter than r prime in y. So here is the illustration of what happens. So we suppose there is a non-trivial dr differential in the random spiral sequence of Z. Recall that Z is a cofiber of F. And then we also suppose that the target of this dr differential y bar comes from the bottom cell, which lies in Y. It's a J extension from Y to the class Y bar. And also, we suppose that the class X bar in Z lies actually in the top cell, which means that there is an H extension from X bar to some suspension of X. Then we conclude that modulo certain boundaries, there is a F extension from X to Y. So let's give the correspondence between this dr differential from X bar to Y bar and F extension from X to Y. We need certain non-crossing conditions to conclude this correspondence. So here is an illustration of how we use the generalized Markov trick. So this is a random spiral sequence for cofiber of nu. Here, for example, we apply the method of secondary operations. We can show a D2 differential from this dot to this red dot. And we know that this red dot lies in the bottom cell, and this black dot lies in the top cell. Okay. Now, in order to conclude that there is a non-trivial nu extension in the random spiral sequence, what we want to show, we want to show that first, the extension from x bar to x is not crossed. So that's obvious because on the E2 term, that black dot lie in the top cell. So that's L equals 0 here. So it's already the shortest extension differential. So there's no crossings here. And in the same way, that's the red dot lying in the bottom cell, which is also detected on the E2 term, which means that here in this extension, m also equals 0. It's also already the shortest extension, so it can't be crossed. So 1 and 3 is not crossing. And what about this differential? And we directly see from here that the D2 differential is not crossed because it is also the shortest differential from the end of the E2 page. So what we conclude? We conclude that this D2 differential corresponds to a hidden extension from the source and target, which means from this black dot, which lies in the top cell, the corresponding dot in top cell have a non-trivial new extension to this red dot, which is the H0P. So using this non-trivial new extension, we can conclude that there is a non-trivial new extension from this dot to this red dot, and we can apply the generalized Leibniz rule to conclude this D3 differential from this D2 differential. But wait, there is a deficiency in this argument. So in our generalized Mahorro trick, what we conclude that is that there is a dn differential from x to y, which lies in the en plus m plus 1 plus EH page. But in order to apply the generalized Leibniz rule, we need an extension from x infinity to y infinity in the E infinity page. So there is a deficiency between this. So we also need a way to stretch our extensions. So suppose we have shown that there is a FER extension with some small r prime. We want to conclude that there is a extension on the ER page of the same kind. We must note that this is not automatic. So in order for this to work, we need another non-crossing condition. Suppose r is greater or equal than r prime. Suppose there is a FER prime extension like dnf ER prime x equals y for some x lying in z r minus 1 st of x, and y lying in z r prime minus 1 minus n plus ef s plus n t plus n of y. We assume that this extension has no crossing of the form dn minus a minus b FER prime minus a s prime equals y prime for any b greater than 0 and a lie between 0 and n minus e of f, and x lie in z r minus 1 minus a s plus a t plus a of x, which is not a r minus 1 minus a cycle. Then we also have a FER extension on the ER page from x to y. So essentially, if our extension is not crossed by certain kind of shorter extensions, we can stretch that extension longer to conclude a F extension in a later page. In particular, that condition is satisfied for this particular new extension, and we conclude that our extension really happens on the infinity page, and we can apply the generalized Leibniz rule. So that's the end of my talk. Thank you very much.